Chapter 15, Day 2, the General Multiplication Rule and Independence. In the last chapter, and I'm just going to highlight as we go, we learned the rule for finding A and B when A and B are independent, which is the probability of A and B equals the probability of A times the probability of B. For example, the probability that you roll a 2 when you roll a die would be 1 out of 6. Okay, the probability that you roll a 2 and then another 2 would be 1 out of 6 times 1 out of 6, or 1 out of 36. And these two are both independent because rolling a 2 on your first try is not going to affect rolling the 2 on the second try. However, now that we understand conditional probability, we can use this general multiplication rule, which is down here, that works whether or not events are independent. And we've used this before as well, such as the probability of getting a boy or a male if it's out of my sticks where I have 10 males out of 30 kids. So the probability of getting a male and then another male, well, the first stick I'd have a 10 out of 30 chance of getting a boy. Assume I got a girl, okay? So my next stick, there are still 10 boys in there, or 10 males, but there are only 29 sticks. So that's this new formula, which says you still multiply them by the probability of the first event times the probability of the second event, but the second event may need to change based off of what you got for the first event. Okay. This rule comes directly from the conditional probability formula we learned yesterday. Below is that formula in green. I'm actually going to scoot it over because here's our formula. And if you decide to solve for the probability of A and B, which is this part, we would just multiply the top and the bottom by the probability of A. And you'd get the probability of A and B, that's this part, equals this part. The probability of A times the probability of B, given that A has already occurred. So this is our new formula. Always works, not just when they're independent. Okay? And it's derived from the conditional probability formula. Let's do some examples. What is the probability of drawing 2 aces in a row from a deck without replacement? That's why this is important, because with replacement, they'd be independent. And that's the probability of getting an ace and an ace, or ace 1 and ace 2. So we're going to use my formula, and that's just the probability of getting ace 1. So there are 4 aces out of 52 cards. Okay. Now it says, assuming that you got an ace the first time, which means there are only 3 aces left and 51 cards left, what's the probability of getting another ace? So to get the first ace, it was 4 out of 52. But to get the second ace, there were only 3 aces left and 51 cards left, which would simplify to 12 over 2652, or a pretty small probability. So it's just using the formula. We've been doing this anyway. Suppose that 23% of Hillcrest students are seniors and 65% of seniors are taking a math class. What is the probability that a randomly selected Hillcrest student is a senior and taking a math class? So first I'm going to define the variables. The probability of being a senior is 23%, and the probability that the seniors are taking a math class is 65%. Notice how I wrote that last one. I said probability, we know they're seniors already, so that's the given, and that they are taking a math class. So given that they're seniors, the probability that they're taking a math class. So I wrote it in the given format. Selected Hillcrest student is a senior and is taking a math class. So it's senior and math, and so we're going to use our formula. That is just the probability of being a senior times the probability of taking a math class given you're a senior. And they've already given us the pieces, so that's 0.23 times 0.65 or 0.1495, about 15%. So they'd already given us the pieces for that. Here's a new problem. Suppose that there are 12 girls on a softball team. 6 of them are freshmen, 4 are sophomore, and 2 are juniors. Okay, and then we're going to draw different combinations. It says if 2 players are selected at random, what is the probability that both are juniors? Before I even start, I'm going to go over here and think about it. Well, the probability of being a junior is 12 out of all of the students. Okay, correction. The probability of being a junior, well, there are 12 girls, 2 of which are juniors, so 2 out of 12. The probability of being a freshman is 6 out of 12, or 1/2. And the probability of sophomore is 4 out of 12. So let's double check. Does that add up to 1 to be a valid probability distribution? 4 plus 6 is 10, plus 2 over is 12. We're good. Now we can answer the question. So it says, what is the probability that if we randomly selected 2 players, they are both juniors? So we have the first one as a junior, J subscript 1, meaning the first one, and the second one. Okay, so that's our formula. Go right back up to our formula, which would be the probability of the first one being a junior times the probability of the second one being a junior, given that the first one was a junior. And now we'll just fill that in. So the chance of the first one being a junior is 2 out of 12. If the first one was a junior, there are only 11 kids left and 1 junior left. So 2 out of 132. We've been doing this for 1.5 units or 2 units, but now we're putting a formula with it. That's the only difference. Question. That neither is a junior. Well, we need to figure out the new probability for that. Probability for junior complement. Well, if 2 out of 12 are juniors, then junior complement is 8 out of 12. And we're going to use the formula. The formula says that that's the probability of the first one not being a junior times the probability of having the second one not be a junior, given that the first one was not a junior. So the probability of the first one not being a junior is 8 out of 12. Assuming that the first one was a junior, so we knew the first one was a junior, there are 7 juniors left, or sorry, assuming that the first one was not a junior, there are 7 not juniors left out of 11. Okay, that was actually one error, and if you look, it stems back from my original probability that the probability of not being a junior is 8 out of 12. Well, there are 12 juniors, so that would actually be 10 out of 12. So if I were to go back and correct this, the probability that the first person I picked is not a junior is 10 out of 12. Assuming that this person was not a junior, now there are 9 not juniors left out of 11, or 90 out of 132. So again, the only thing that's really new is the notation with the formula. We've been doing this the whole time. C says at least 1 junior. As soon as you hear at least 1, that should trigger in your mind 1 minus the probability of none, because at least 1 would get kind of confusing. You could have a junior and a sophomore, a junior and a freshman, a sophomore and a sophomore, a freshman and a junior, or a junior and a junior. Okay, this one should actually be sophomore and junior. So we have junior, sophomore, sophomore, junior. Junior, freshman, freshman, junior, or they could both be juniors. So you could find all those probabilities separately and add them up. But much easier is 1 minus the probability of none. Well, we just figured out right here the chance of both of them not being a junior, or the probability, this is the probability of none, no juniors, right, is 90 out of 132. So we can just do 1 minus 90 out of 132, which gives us about 0.318, or 31.8%. And if you did it the long way, you would get the same answer. Okay. but it's definitely just easier to do 1 minus the probability of none. Finally, it says, what is the probability that they are the same grade? So I've already started looking at it right here. They could both be sophomores, sophomore 1, sophomore 2, both freshmen, both juniors. This means sophomore and sophomore, freshman and freshman, junior and junior. And then this union means or. So they could be 2 sophomores or 2 juniors or 2 freshmen or 2 juniors. And we can go back and just use our formula, which would be, that's the probability of a sophomore times the probability of another sophomore given that the first one was a sophomore. Or we could have a freshman times the probability of another freshman, or using the formula we could have a junior times the probability of another junior given that the first one was a junior. Okay, and if we went ahead and just added those up, probability of a sophomore, well, there are 4 sophomores, so 4 out of 12. If the first one was a sophomore, then it would be 3 out of 11. Or for freshmen, we've got 6 out of 12 and 5 times 11. And then again, or for juniors, 2 out of 12 or 1 out of 11, which would give us the probability. And I haven't crunched those numbers. Okay, reminder. When we are sampling without replacement, successive selections are not independent. That's why this denominator changes. When population size is known, you should adjust the probabilities accordingly. However, on, say, last time's homework for M&Ms, we didn't know the population size, so we just used that, say, 10% were green without accounting for that each time we drew out an M&M. Next thing. Also, we can now formally define independence. Events A and B are independent whenever the probability of A or probability of B given A is the same as the probability of B given A complement, which is the same as the probability of B. That is, that knowing the outcome of event A does not change the probability of event B. Whenever you are asked about independence, this is the definition you should use to justify your answer. Okay? Also, we can see that the original multiplication formula is just a special case of the general formula, since the probability of A times the probability of B given A simplifies to this when they are independent, right? Because we said the probability of B given A is the probability of B, so the same thing. This, if they're independent, the probability of B given A is going to just be the same as the probability of B. If this is getting confusing, don't worry, we'll just do lots of practice and it'll click. Finally, it says, using examples from yesterday or last lecture, were being male and surviving independent on the Titanic? And the answer is no, it's not independent. In fact, we saw that if you were a male, you were more likely to die because they put the women and the children first on the lifeboats. And it was also not disjoint. Disjoint would be that the probability of male and surviving equals 0. Well, there were males that survived, so it's not disjoint. And I will clarify this with a handout next time. Okay. Lastly, notes. If event E and F are independent and the data we have is from a random sample, then the probability of E given F is the same as the probability of E, but it could be a little off. And it's going to be off because of sampling variability. Okay, and we'll talk about how close they need to be in chapter 26. I'm going to go to the next video for our last examples.